Hello everyone. In this video, I'm going to talk about one of the key concepts in linear algebra, that is vector spaces. Before going to the definition of vector space, let me refresh few terms of linear algebra. First one is binary operation. Binary operation. It's a function or it's a mapping which combines two elements of the set to produce another element of a set. Suppose star is a binary operation, then it combines two elements of the set, say G cross G gives G. Suppose A comma B belongs to G, then the binary operation star defined like this, say A star B also belongs to G. Next is group. A non-empty set, say G, is said to be group under the binary operation, some binary operation star, if it satisfies these four axioms. Say let A comma B belongs to G, then the first axiom or first property is closure property, that is for all A comma B belongs to G, A star B is in G. If that is true, then closure law is true. Next property is, say for any element E belongs to G, then that implies an identity element, okay? Then A star E is equal to E star A, which is nothing but A. Its existence of such element, that means identity element exists. And then for all A in the set G, there exists B in G such that A star B is E, and which is same as writing B star A. That means inverse exists for any element in A, or in fact for all element in set G. Then the fourth property, it's just associative property. For all A comma B comma C belongs to set G, A star B star C is same as A star B star C. This is associative property. If all these properties are true, then we say set G is a group under the binary operation star. If the fifth property, that is commutative property, is true, then we call G as an abelian group. Means for all A comma B belongs to G, if A star B is same as B star A, then commutative property holds good. Then we are calling G as an abelian group. So that is group. In case of a group, we always deal with the single binary operation, either addition or multiplication. But when it comes to rings, we are dealing with two binary operations. Rings, we are dealing with two binary operation, addition and multiplication. Even in case of fields, what is field? In fact, in vector space is always defined over a field. That field can be a real number or can be a complex. Field is a non-empty set. In fact, it should have at least two elements, one identity element for the multiplication and another identity element for the addition. So field, it's a non-empty set which has at least two elements, and it is a abelian group under addition and abelian group under multiplication. Along with that, here addition distributes over multiplication and multiplication is distributive over addition in field. I can give you some examples for field: set of real numbers, set of complex numbers, Q. They are nothing but infinite fields. Infinite fields. If I take, say, set of primes for addition and multiplication, then this forms a finite field, set of primes. So in general, if I consider any binary operation, then say we always deal with the elements of a same set. Like if I take addition as a binary operation, I'm defining it as, say, from set of real numbers cross set of real numbers to set of real numbers. Means elements from this set I'm taking and I'm doing the binary operation addition. The resultant element is in set R. When I consider multiplication, in fact it is always written as dot. So if that is the binary operation over R, then I have to remove 0 from that. So I am writing it as R star, and the element also belongs to R star, where R star is nothing but set of real numbers minus 0 in case of multiplication. So in general, when we consider a binary operation in case of groups or fields and rings, we deal with the elements from the same set and gives the elements from that set only. But when it comes to vector space, what happens is, if star is my binary operation, I'm taking two sets, that is, one is F, let us take, and another is set V. F cross V gives elements of set V. See, in these cases, I'm taking only one set, and from that set only I'm taking elements and I'm applying the operation addition or multiplication, and the resultant element is in this set only. Okay, so these are nothing but actually internal binary operations. But when I take two different sets, okay, and I'm applying the binary operation, say star, I'm going to get the element of one set. Suppose I'm taking alpha from F and say small vector V from V, then the ordered pair alpha comma V gives me alpha star V, which belongs to set V. Okay, so this is an example for external binary operation. Means I'm taking elements from two different sets and I'm applying the binary operation, and the resulting element is in one of the sets. See, always I should write like this. If I write it in the reverse order, then the ordered pair is reversed, so it has got some other meaning. Okay, ordered pair means you need to write it in order. So this external binary operation I'm using in vector space. So we define vector space. What is vector space? A nonempty set V is said to be a vector space over a field F if addition is defined like this: V cross V to V, and multiplication is defined like this: F cross V to V. If a non-empty set V is said to be a vector space over a field F if it satisfies the following condition. The first condition is Set V over the binary operation addition is an abelian group. An abelian group. Second one has got two sub axioms. Same for all alpha belongs to F, for all alpha, in fact, for all alpha belongs to F, and V1 comma V2 belongs to V, then alpha dot V1 plus V2 is nothing but alpha V1 plus alpha V2. Similarly, for all alpha comma beta belongs to F and V belongs to V, alpha plus beta into V gives me alpha V plus beta V. Then the third axiom is for all alpha beta belongs to F, alpha into beta V is nothing but alpha into beta into V, and there exists an unit element 1 into V is nothing but V. This is true for all V belongs to V. Okay, if these conditions are satisfied by the elements of the set V, then V is called a vector space over the field F. Remember one thing, this over a field F we are defining, no? It's not necessary that it has to be a scalar element set. It can be a complex also, then it becomes a complex field. We usually deal with the real field, means a field is taken as a set of real numbers. So generally we can say vector space is nothing but a space of vectors where vectors can be added and can be scaled. The elements we are taking over a field F, that field can be a real number, can be a complex number. Here we deal with the real field. Let me give a few basic examples of vector space. Suppose if I consider, say, E as a field, okay, it's a field, and it's a field, let me call it as F, okay, this is the subfield. Now, this field forms a vector space over the field F, over the subfield F. This forms a vector space over F. E forms a vector space over F. In general, if I take set of real numbers, okay, set of real numbers, it's a subset of set of complex numbers. When I consider set of real numbers are the subset of set of complex numbers, so I can say C forms a vector space over set of real numbers. Similarly, I can say a set of real numbers is a subset of set of real numbers itself. So I can say this also forms this also forms a vector space over the field R. Similarly, a set of Q forms a vector space over C. Similarly, complex numbers over complex numbers, R over R, everything. So this forms a vector space. set of complex numbers is forms a vector space over R, and set of real numbers forms a vector space over R, like that. Now, say when I consider my field as, say, set of two tuples, say that is R2, we write superscripted R2. How is any element in R2? It's an ordered pair x comma y such that each x and y belongs to set of real numbers. Okay, now this R2 forms a vector space, is a vector space over set of real numbers. You can check, this is my first example, let us take. You can check it out. Say, how is the addition defined over here? Elements from R2 I am taking, cross R2 gives an element of R2, and when I consider multiplication, elements from set of real numbers I am taking along with R2 gives me an element of R2. Let me take, say, U, an element from R2. How is that? It's a vector, or can be written as a ordered pair. Let me name x1 comma y1 and V as x2 y2. Two tuples, set of two tuples, so it's an ordered pair. Of course, U and V are from set R2, and I'll take their sum U plus V, which is nothing but x1 comma y1 plus x2 comma y2. How I have to add? I have to add first terms. So x1 plus x2 comma y1 plus y2. Again it is a two tuple and it also belongs to R2. So first axiom is true, and for any alpha belongs to real number set R, then alpha into U is nothing but alpha into x1 comma y1, which is nothing but alpha x1 comma alpha y1, which is also a two tuple and it belongs to R2. Thus I can say that R2 forms a vector space over R. Similarly, we can give examples saying Rn forms a vector space over R.